Any questions, first of all? Lots of questions about the homework that didn't have adequate measurements, etc.
Yeah.
Okay, well, is there anything I can do to help right now, or no?
Can you actually go over 4 if you don't
Yes.
mind a little bit? That'd be very
Okay, let's go through 4. I can do that. So my guess is that the problem is that question once had weight, and then when I put it in this set of problems, there was no weight, but in the solution there still was. Something like that happened. Okay, so it's a cantilever beam on the right. And what do you think when you have a cantilever beam on the right? Yep, you can skip all the external load calculations and just go right to the internal loads. Although you can't use those endpoint checks on the right if you don't calculate the external loads. So that's one reason to do it. 6,000 newtons per meter. And then this is 1.2. And this is 1.2. How many places are there where the subfunctions are going to change? Well, there's the 2 endpoints and then the middle. So n is equal to 3. And so we're going to have 2 cuts. Cut 1 is for x values between 0 and 1.2. And no matter what x is in this range, the distributed load goes all the way along the member. And then we have these internal loads. And then in the solution, I had another distributed load acting that I guess would have been the weight. Okay, so think about this rectangle. The centroid's right in the middle. The height is 6,000. The width is x, because this is x. And so the total force is 6,000x. So I'll redraw that free body diagram. Now that I've chosen the body to isolate, I've chosen this piece to isolate, I can treat the distributed load as a point force. So we have a downward force of 6,000x acting right in the middle. So this distance is x over 2. And then the internal loads. So Newton's second law says 0, negative 6,000x, plus t negative v is equal to zeros. So t is equal to 0, v is equal to negative 6,000x. The moment equation, the 6,000x force has a moment arm of x over 2. And that would cause a clockwise rotation around that point, so it's negative. And then plus m minus vx equals 0. So m is equal to 3,000x squared plus vx which is negative 3,000 x squared. Okay, that's the first cut. Any questions about that? You can do the derivative checks. dm dx is equal to v. That one works. dv dx is negative 6,000. Negative dv dx is positive 6,000, and that's equal to q. Q is that constant function of 6,000, so those both work out. You could do the endpoint checks on the left endpoint. You can't do them on the right because these subfunctions that we just found don't hold for x values all the way to the right side, but they do hold for the left end. Okay, so now cut 2. We're looking at x values from 1.2 to 2.4. Any x value we choose in this interval is past the end of this distributed load. So no matter how we draw our cut, the entire distributed load is present in this picture, and and the right end doesn't have a distributed load acting. Okay, so we have something like that. And this distance, what's that distance? Yeah, that's 1.2. No matter what x is, we have a full 1.2 meters of this distributed load. This distance is x. And so if you think of this rectangle now, it has a height of 6,000. It has a width of 1.2. The centroid's right in the middle. In other words, this distance is 0.6. The total force is the area, so 6,000 times 1.2, or 7,200. So now I'll redraw this with that distributed load represented as a point force. So we have a force of 7,200. This distance is 0.6. This distance is x, and then we have the internal loads. So Newton's second law says 0, negative 7,200, plus t negative v is equal to zeros. So t is equal to 0, v is equal to negative 7,200. And the moment equation, you have 0.6 times 7,200. That's the about point, so this would cause a clockwise rotation. And then we have plus m minus vx equals 0. So m is equal to, what's 0.6 times 7,200? 4320. Yep. So 43, so we have negative 7,200 x plus 4320. And dm dx is equal to v. Negative dv dx is 0, and that's because for these x values on the second that the second cut represents, there's no distributed load. So one thing you can always look for is if your cut is representing points that don't have a distributed load acting, that shear force always has to be constant. Any questions about that?
I have a question.
Yeah.
So for internal problem,
Mm-hmm.
if I did 5 check and it's all correct, does that mean the result I get is always right?
No, it doesn't mean that. It's just every time you look for something that has to be true and you see it in your answer, it just gives you more confidence. But no, it doesn't. Right. Yes.
Do you do or talk about under 3B on the second slide?
3B. Yes. Oh, yeah. Okay, so this one looks the same except the distributed load chunk is moved over to the other side. The value is 25,000 newtons per meter. This one, I think if you calculate those components, you get 17,677, negative 17,677. And this distance is 0.5, and this is 0.5. Okay, so the subfunctions change at the two endpoints, and then the distributed load changes in the middle, so n is equal to 3, which means we have 2 cuts. The first cut, there isn't anything too difficult going on, so let's just do the second cut. So cut 2 represents x values between 0.5 and 1. And there's going to be some part of that distributed load acting, no matter what your x is in that range. This has a value of 25,000. We have that same force vector over here. And then we have the internal loads. Okay, well, we need to figure out, excuse me, we need to figure out some of these distances. This is x. This, what's the distance from the left end to where that distributed load starts? That's 0.5. Stop me if any of this is, if you need a longer look at any of these things. Okay, so now so let's look at that rectangular distributed load. We know its height is 25,000. The centroid's right in the middle. what's the base? What's the length of this shape? It's not 0.5 because it would be 0.5 if our x was equal to 1. Yeah, this is going to be x minus 0.5. Okay? And so what's this distance? Well, actually, let's not even, that's not really the distance that we want. I suppose we could do it that way. I think the way, instead of thinking about it like this, I think an easier way to do it is, you know that it's going to be at the midpoint of 0.5 and x, right? And I think I said at one point the most important thing in this whole class is to remember is if you ever have to find a midpoint between 2 points, you just average them. So this is x equals 0.5. This is x equals x. Average those two and it gives you the midpoint. So x plus 0.5 over 2 is going to give us the location where this force is applied. There are a few ways you can think about the geometry, but I think that's a nice, quick way. It's the average, so yeah, x. So we're averaging x and 0.5. So x plus 0.5 divided by 2. There are some other ways you could think about it too, but that's a quick one. Anytime you have to find a midpoint between 2 points, think you're going to average two points. Okay, so we have a downward force that's equal to, so the total force is equal to 25,000 times the quantity x minus 0.5. So I'll write that as 25,000 x minus 12,500. We have the point force over here. And then T, V, M. And this distance is x plus 0.5 divided by 2. So Newton's second law says 17,677, negative 17,677, plus, this is the magnitude of the force. We want it in the negative y direction, which means this is going to be 0, negative times that, negative of that. Plus t negative v is equal to zeros. So t is equal to negative 17,677. V is equal to negative 5,177. Is that right? And I'm missing some stuff here. Negative 25,000x. Is that right? But this is This one's negative. This is a negative, double negative. Okay. Ha! For once I was right and you were wrong. Okay, and then the moment equation. Okay, so now this is going to get messy because we have an ugly force and we have an ugly moment arm. So we have a moment arm of x. Let's see. Yeah, let's write it as x plus 0.5 over 2. That's the moment arm. And the force is 25,000 x minus 12,500. And if this is the about point, that would be a clockwise moment. So negative. And then we have plus m minus vx is equal to 0. And m equals ... Left as an exercise to the reader. Any questions about that? So you got to FOIL it out. Have you heard people, like teachers, talk about not liking FOIL? They don't like FOIL because they want you to think about what it is, not like this memory device. I don't mind saying FOIL. But yeah, you have to multiply out the, distribute all those across. Any other questions about that one? Any other questions on the assignment you'd like to see? Yeah. For number 6? Yeah, number 6 is a hard one. Yeah, that's what Robert was just telling me. Sorry about that. So I guess in the solution there you could figure out what they were probably. And no angles either, huh?
Yeah, there's no way to set that up the way the problem's given.
There's no way?
Well, there's no dimension.
Oh, there's not enough information, right.
There's no length on the
Right.
joints are, so you can't.
That's right. So this is number 6. Yeah, sorry about that. Does anyone remember from the solution what those dimensions are? I would guess 1 meter each and 10 degrees. What? Okay. Okay, so each of these is 1 meter long. And this angle is 80 degrees and it's symmetric. Let's do it like that. So I'll call this member 1 and this member 2. And so member 2 is the one that has the pulley attached to it. Okay, so member 1. Okay, point. Yeah, right. So I wonder, does that come into it?
I also have
It does.
pulleys.
It does.
I remember
Yep.
there was one problem, and you draw the free body diagram for the pulley
Mhm.
separately, but in the solution you didn't.
Yeah.
So is that like you treat
I think
loss?
In that other question, we isolated the pulley because I asked for the loads acting on the pulley. I don't think you would have had to do it. In this case, I don't ask you for that explicitly, so you don't have to do it, but you could. Like if you were asked for the loads on the pulley, you could do it just the same way. But yeah, what? Question? Okay, so let's say the diameter is 0.1. And let's call this A and this B. So on member 1, there's a reaction RA. At the midpoint, there's a force on 1 by 2. And then at the top, there's a force of 300 going to the left. Any questions about that? I don't have much room left, so this is a perfect opportunity to bring out the travel version of the pancake table. Okay, so let's say the about point is here. So the force RA is at the origin, or is at the about point, so there's no row vector. The force vector is RAX, RAY, cross product is 0. Then the force F12 the row vector is 0.5 times cosine of 80, 0.5 times sine of 80, which is what?
0.087 and then 0.182.
Okay. And so the cross product is 0.087 F12Y minus 0.492 F12X. And then the last one is the 300. That is at twice this, 0.185. Is that right? 174, 0.985, right?
Yeah.
And then the force is negative 300, 0. So what's 0.985 times 300? 295.5. So the first three equations, the first one says RAX plus F12X minus 300 is equal to 0, so I'll just move this over and make it positive 300. The second equation says RAY plus F12Y is equal to 0. And the third one says negative 0.492 F12X plus 0.087 F12Y is equal to negative 295.5. And then we'll go to body 2.
Did you put the origin at RA or?
The way I did it there was I wasn't even thinking about origins, but you could, that would be fine. I guess one way to think about it, if you're just thinking about the row vectors, is think about the origin being at the about point and just finding the vector, the position of the point where the force is applied. Okay, so now we're going to body 2. There's a force RB. There's a negative force on 1/2. And then there are 2 of these tension forces, there and there. And those distances are 1 meter apart, 0.1 meters apart, sorry. And this is a vertical distance. I mean, I'm just saying that's not a diagonal distance. The distance in, then the height would be something less than 0.1. The height distance. You know what I mean?
I mean,
But that's a vertical.
It makes sense as according to the beam.
Mm-hmm. Okay, so rho F M I'll put the about point at B. So no row vector for RB. Then the negative F12, that's acting at negative 0.087, positive 0.492. The force vector is negative F12x, negative F12y. So the cross product is 0.087 F12y plus 0.492 F12x. Then I'll first do the one at the top. That
In your solution, you have used the same x value, and you only changed the y value by 0.1. So you gave it no width. Or maybe
Yeah.
negligible.
It's like this. The beam, let me draw the angle more exaggerated. So that cable is going to come off at the top and the bottom, no matter what the angle of that beam is. So yeah, these two are going to have the same x position, and their y position is just going to differ by the diameter of that pulley, which is 0.1. The row vector for the top cable force is negative 0.174, positive 0.985. The force vector is 300, 0. And so for that you get 295.5 negative. And then for the lower cable force, you have this just minus 0.1. So you get negative 0.174, 0.885. The force is 300, 0. Can someone tell me what that is? 0.885 times 300? Negative. Okay. Yeah, subtract 30. Okay, so now equation 4 says RBX minus F12X is equal to negative 600. Equation 5 says RBY minus F12Y is equal to 0. And equation 6 says 0.492 F12X plus 0.087 F12Y is equal to, what's that? Okay. So now let's do just one of these, the internal loads for one of these. I don't care which one. Anyone have a preference?
I'm gonna say the one that where you take it down to negative 80, where the change in theta is negative 80. So
Okay,
that'll be the
negative 80. Okay, so that one is going to have one extra cut, but that's the slightly more complicated one. But it looks like this. Does anyone have a solution for that? Negative 870. And then what?
negative 1542.
Okay. And then for RB,
I got negative 570,
negative 570. Negative 15. Wait, positive 1542? The one at the bottom is negative and this one's positive?
I have both as negative, but
Mm.
I had different numbers for 1 and 2. I mean, like,
Oh, okay.
I don't know if that would make a difference. Yeah, I don't know both.
Well, let's see. This seems believable to me. I think it's like this. Okay. All right, so we want to go from this coordinate system to this coordinate system. And for that, theta is equal to negative 80 degrees. So the rotation matrix Q, cosine of negative 80, sine of negative 80, negative sine of negative 80, cosine of negative 80. So I think that is 0.174, negative 0.985, positive 0.985, positive 0.174. So the 300, yep.
So that those 570 is for the other one, but this one should be 269 or 270 and then 1542.
Oh, it should be what?
260. You can use 270.
For this?
No, for that.
This?
Yeah.
270? Oh, yeah. Right.
I have a question.
Mhm.
For rotation matrix. So your way is to make original coordinate system rotate clockwise, so the angle would be negative 80.
Right.
So is it okay to rotate clockwise? The angle would be 100, but the new origin would be at the bottom of the beam. Is it okay? Will I get the same
Yes,
results?
that's right. Yep, exactly. That's perfectly fine. The answers won't match because your x value, x equals 0, starts at the opposite end, but they mean the same thing. So if you, yeah. Okay, so the 300 Newton force in the original coordinate system, okay, so multiply the rotation matrix. Times this force in the original coordinate system, which is 300, 0. Can someone multiply that? Ooh, I know what this one's going to be. This is going to be 295.5. What is it? 52.09. Okay, and we have two of those, so, and then we come to this one. At the middle, we have that same Q matrix times negative 870, negative 1542. What do you get for that?
Yeah, 1368 and 1125.
Okay. And then at the joint B, multiply Q by 270, positive 1542. What do you get for that?
Negative 1472.
1472?
Yeah.
Okay.
And 534.
Okay. So now that we have this expressed in the rotated coordinate system,
How do you know where each of those goes? That's my basic question.
oh, okay.
Let me use that.
Um,
So I can put the rotation matrix in my calculator and get the right numbers.
okay. Well, what we're doing is switching to a point of view, this guy's point of view. Okay, so those two 300s are going to be the ones on the left. This will be at the middle, and this will be on the right.
And you do the same thing. So on the other one, so on the other body, would you be looking from the bottom instead? Or would you
So so you always have the choice, and usually usually you just do the one where usually I just do the one where you have to rotate it the least. But like Banan was just asking, couldn't we do this as a rotation of 100 degrees of the coordinate system and have the coordinate system like that instead of like that? Then in that case, this would be the one at your all the way at the left. This would be the one in the middle, and you'd have these two on the right end.
I guess it have something to do with the origin, because if you know ways, the origin is the top of the beam, but if rotate counterclockwise, the origin will be the bottom.
Well, your new right end is always going to be in the positive x direction, you know. So depending on, so if you have your positive x direction going this way, then this has to be the right end and this has to be the left end. If you flip it this way, your x-axis is going this way, that has to be the left and that has to be the right. Okay, so each one of these is 52.09, 295.5. Then in the middle, you have 1368, 1125. And then at the end, you have negative 1472, 534. How many places are there? Like, what's the n for this? 4. So you're going to have 3 cuts. One that just represents 0.1 worth of x values between 0 and 0.1, then the one up to the midpoint, and then the one after the midpoint. Any other questions about that one? The good news is once you get to the internal loads on problems like this, these are the easiest internal loads problems because you don't have anything but point loads. The bad news is everything else. But really, I think these are cool because, I mean, I think structures are cool. Like the approach to structures can let you, I mean, you can go outside and find all these things and calculate the forces. And now this gives you this extra step you can take. Once you find a structure you want to calculate, you can actually go in and see where in the object this thing is going to have to deal with the most internal loads, is most likely to bend, most likely to break, that kind of thing. So I like this kind of stuff. Any other questions about the homework? Just give me your papers. I'll just do them. Just put your name down. I'll finish your homework. Not really. Okay. Well, let's take a break, and then we'll do. We'll start with friction at 5 after. So we're starting with square threaded screws. Who remembers what the other things we're going to do with friction are?
Belt friction.
Belt, and then 2 kinds of bearings. Yep. So this is the first one. Friction 1. Smoothness lost. Okay, so here is a square threaded screw. And that is distinguished from, so here is a thread that's not square. You follow what I'm getting at? So we're going to do these, and we're not going to do these. These non-square threaded screws are easier to machine, and so for applications where there aren't going to be, where these aren't going to be supporting big loads, these are used. Square threaded screws are better at supporting big loads, like, for example, in a car jack, not a car jacking, but like the thing. You use square threaded screws because it has to support a really big force applied parallel to the screw. If you apply too big a force with a thread like this, two things happen. One is, you can imagine when you get towards the really thin part of the thread, it's susceptible to breaking. And the other thing is, because of the directions of the normal forces acting, when you apply a big force in this direction onto a screw that's not square threaded, you have this effect. This screw causes a bursting apart of the path that it's riding on. And so that's the reason that, this is cheaper to make. You just use a tap, screw it in there. This is harder to make, but it can support bigger forces. Okay, so what happens when a thread slides along a path? So remember, square threaded screws are going to end up being a calculation of a block sliding along an incline. And that seems like kind of a stretch, They don't, at first glance, they don't look very much alike. So think about what's happening with this thread. If there's a force acting on the screw this way, that force is pushing, like you can think of that thread as riding along a threaded path like this. Follow what I mean? And on the other side too. And so if you tracked a single point on this screw as it went up on that thread that it's connected to, that it's touching, like if you painted a point here, it would slide in a helical path around the shaded path. So remember, one thing about drive friction, it's sort of a surprising fact. It's not totally true, but this is how we do the calculation. About the force of friction equal to the coefficient times the normal approach, is that the surface area of contact doesn't come into that equation anywhere. So it doesn't come into the calculation. It's very confusing that that's the case, and actually it turns out that's not entirely true at all, but that's the way you do this calculation. And so the fact that you have, I mean, if you have a long screw, you have several inches of path on the screw thread that's sliding along several inches of path on the thread that it's touching, right? So you have this big amount of area, but we don't care about that. We can shrink it down to a single chunk without changing the calculation at all. So reimagine this contact as, so think of the screw like this, where all of its thread is just concentrated in one little spot. And then that that concentrated thread slides up this path on the thread that it's connected to. Who follows what I'm getting at here? Nobody? Okay.
That's a screw. You have to think about it being
So
path being. Oh, so
the path is like the nut. The path is the nut, or the. This is the. This little block is the screw thread concentrated into one spot. You can do that because the surface area of contact doesn't matter in this calculation. Okay. Well, if you look at it from the side, so imagine what this looks like to this guy. What he sees is the thread from the nut with the thread of the screw sliding up or down. Okay, so the problem that this boils down to is you have an incline with some angle, and you have a block that's being pushed up or down this incline by a force Q, capital Q, while being subjected to a force, I'll call it W, that's the weight of the thing that you're lifting or lowering. Yeah.
Sorry about this, but do you mind scrolling up just a
Yes.
right underneath where it says he sees right there,
Yeah.
could you kind of re-explain where, you're talking about thread of screws, thread of nut right there, where you have the triangle with
Yeah.
the block sitting on top? I'm having a tough time
Okay.
visualizing that.
Well, so imagine him looking at.
Oh, I
What-
get that. I'm talking
okay.
about right underneath where it says
Yeah.
he sees.
Well, so this path that it's sliding along here
Yeah.
is the wedge. It's the incline, and this little chunk of screw thread that he sees is this block.
Okay.
He's seeing this thing just sliding into the page up that ramp,
Okay.
There'd be a top
and this
and
is
a
what
bottom.
it looks like.
There'd be a top and a bottom, because there's a groove, but it's just hard to draw it. Is that what you're
Yeah, so as far as that wedge being solid, kind of, yes, you're right. So, but this is just one little chunk of the thread of the nut, and this is the screw sliding either up or down the thread of the nut.
I got a silly question.
Yeah.
I still have no idea what is a square stress.
Okay.
Could you Google some pictures?
Some pictures? Yes. I'll look for it after class, okay? But I guess it's just saying that the two surfaces of the thread are parallel to each other, whereas here the two surfaces of the thread meet at an angle. See how, okay, let's talk about it after. That's okay.
Ask one more question.
Yeah.
So what does Q represent again?
Q is just, for now, it's just a force that's pushing it up or down. It's not really anything physical yet.
You don't really know where that comes
Right, but we will talk about that.
from. Okay.
But, okay, so, let's do a problem, and I'm going to come up with a general formula, but the way I want you to be able to do these problems is to sort of derive it. You can put numbers in, but you have to be able to go through this derivation. It's not too difficult or complicated. But I know, just trying to remember a formula isn't going to help later, so I want you to sort of understand what's going on. Okay, so let's say that we have that situation that I just talked about. We have a vertical W and a horizontal Q. And we want to know what's the Q required to start motion up the ramp. And B, what's the Q required to start motion down the ramp? In that case, everything would look the same, except your Q would be going this way. Anyone have a sense of which one of these Q values is going to be bigger? Going up is going to be bigger because going down, Q is sort of working with the weight of the object, and going up, it's fighting against the weight of the object. Okay, so for part A, let's draw a free body diagram of the block. Oh, and I need to tell you that the coefficient of static friction is mu sub s, so that's going to come into our calculation. All right, so there's a weight force acting down. There's a Q acting to the right. There's a normal force. And then, which way is the friction force acting? It's fighting against this Q, so it's acting down the ramp. And that has a value of mu sub s times n. And we're going to use a coordinate system that's rotated with the ramp. So there's a couple of ways to you can use trigonometry, use triangles to express W and Q in this rotated coordinate system, or you can use a rotation matrix. It's fine with me however you want to do it. I'm going to use a rotation matrix. So express W and Q in the rotated coordinate system. So for W, we're going to take this matrix, cosine theta, sine theta, negative sine theta, cosine theta, and multiply it by W expressed in the non-rotated coordinate system. So that's 0 W, negative W. And so in the green coordinate system, you have the vector negative W sine theta, negative W cosine theta. Any questions about that?
It's negative W because we don't have the mass, right?
It's negative W because, like why didn't we put the, because that's given as a force instead of as a mass. And now we're going to do the same thing with Q. So we take this rotation matrix, and multiply it by, in the non-rotated coordinate system, what are the components for this vector? Q0, yep. And so you get Q cosine theta, negative Q sine theta. And now we can write Newton's second law. So negative W sine theta, negative W cosine theta, plus Q cosine theta, negative Q sine theta, plus, what are the components for the normal force? 0n. And what are the components for the friction force? Yep. So negative mu n, and then 0 for y. Bless you. And that's equal to 0 because we're looking for the spot right where motion is about to start. So now you can solve for, we want to find Q, so we can solve for the variable Q. If this is equation 1 and this is equation 2, let's use equation 2 to express n as equal to q sine theta plus w cosine theta. And then we'll insert that into equation 1. And we get negative w sine theta plus q cosine theta minus mu sub s times the quantity q sine theta plus w cosine theta is equal to 0. And now we can just solve for q. So you get q is equal to mu s times all that stuff in parentheses plus w sine theta and this should still, let's see, so now what, I have to divide by cosine. Oh, I do. Oh, I do have q on both sides. Yeah, right, so, yeah, that's not the way to do it. Yeah, so get the q's together. Okay, so q cosine theta minus mu sub s q sine theta is equal to w times the quantity sine theta plus mu sub s cosine theta, and then q is equal to w times the quantity sine theta plus mu sub s cosine theta, all divided by quantity cosine theta minus mu sub s sine theta.
Did you divide that right? Because if you divided it, because q isn't multiplied with mu sub s. Oh no, yes it is. Okay, never mind.
Okay.
Yep.
I think that's right. I think that's right. Okay, and you could go through a similar thing to figure out the q that's required to make it start moving down. So for part B, the free body diagram looks like this. W is still the same. Normal force is still the same. But now the Q has to be going this way. And the friction force is counteracting Q, so it's this way. And you can go through the same analysis, and you get that Q is equal to W times the quantity mu sub s cosine theta minus sine theta divided by cosine theta plus mu sub s sine theta. Okay, so let's look at these two formulas and just make sure. We expect this Q value to be bigger than this one. Well, notice that on this one, the numerator is bigger going up than it is going down. And the denominator going up is smaller than going up than going down. So this one has to be a bigger force. And this one has to be a smaller force. And that's what we'd expect, because like I said, if the block's sliding down the ramp, Q is working with the weight. If it's sliding up the ramp, Q is fighting against the weight. Any questions about that? Okay, so there's two more things. Two last items with this. The first one is that that Q is a mathematical thing. It's not a real force that's applied to this thing to turn it. It's not a real force. What's really the load that's really applied to turn this screw in the nut is a couple. A couple about the screw's long axis. And so we need to be able to go from the applied couple to that force, that fake force Q. And then the second thing is that these screws aren't, like if you want to buy a square threaded screw, the parameter that you give to buy it, unfortunately, isn't that angle theta. I mean, for calculations, that would be nice, but instead you're given a value of a pitch or a lead. And so we need to go from the lead or the pitch to theta. So the first one is the relationship between Q and the couple M. And so if this is the screw, and this distance is the radius r, that fake force Q times r has to be equal to the couple. So if you're given a couple M in the calculations, you can use that Q is equal to M over R. And then the second item yeah. Yep. R is the is from the center of the screw to the outside of the thread. Any other questions about that one? And then the second one is, how did I say this? So the relationship between the lead and theta. If you, okay, so let me draw a blown up picture of the screw. So imagine you send an ant or whatever walking up the okay, so this ant's walking around the thread. Okay, he's going this way. No, those were torn off. So if he's making this trip around, he's going to go up here, he's going to go up the other side, and eventually he's going to end up directly above where he started, right? This distance, this vertical distance, is called the lead. It means something a little different than the pitch. For a lot of screws, it means the same thing as the pitch. But there are some screws where this ant wouldn't show up on the next. If he took this track around, he wouldn't ever come up here. He'd skip that one and end up on this one because some screws have this double thread. And so the lead measures the vertical distance change for something as it follows that path around. So if we call that lead lowercase l, you can imagine this thread being straightened out, and you would get, if you straightened out one entire rotation around the screw of this thread, you would have a horizontal distance that's equal to 2 pi r. That's the circumference. And over here you'd have the lead. And this is the angle that you want to find. So theta then is equal to the inverse tangent of L over 2 pi r. Any questions about that? Okay, let's stop there and I'll finish this stuff tomorrow.